That glass plate you hold in your hands, the screen of your cell phone, is a window. A window to knowledge, to communication, to the world. But it's much stranger than you imagine. You're looking at a piece of matter that, strictly speaking, shouldn't exist. At least not according to the simple categories we learned in school. It's not a solid, it's not a liquid, and it's definitely not a gas. It's something in between. It's a state of matter so paradoxical that it's been named liquid crystal. A name that is a contradiction in itself. How can something be ordered and structured like a crystal, but at the same time flow and take the shape of its container like a liquid? And yet, it is precisely this impossible property that allows your screen to create the images you see. Each pixel, each point of color that forms a family photo or a cat video, is the result of manipulating a material that refuses to be categorized. You're not just looking at a screen, you are witnessing a state of matter that defies logic, a substance that lives on the border between order and chaos, and which we have learned to tame with electricity in order to paint with light itself. Think about how magical and routine this has become. We touch an icon and a new image instantly appears. We slide our finger and the world moves at our command. We accept this magical window as a given. But how does it work? There are no tiny projectors or microscopic artists painting each frame. The screen itself is the source of the image. It's a surface that can be transparent at one point and opaque at another, red here and blue there, all changing thousands of times per second. How can a piece of glass have such fine control over the light passing through it? The mystery lies not in the glass itself, but in the incredibly thin sandwich filling that makes up the screen. Between two layers of glass, there is a very thin layer of this bizarre substance, liquid crystal. This material doesn't generate light, it manipulates it. It acts as a microscopic gatekeeper for the light coming from behind your screen, a backlight usually made of LEDs. Each pixel is a tiny gate, and the liquid crystal is the guard that decides whether the gate opens or closes to let the light through. And the command to open or close it is a small electrical pulse. I've spent my life fascinated by how things work at their most fundamental level. The joy of peeling back the layers of a phenomenon to reach the underlying physical principle is one of the greatest thrills there is. And liquid crystal displays, or LCDs, are a wonderful playground for the curious mind. They combine optics, electromagnetism, and the physics of matter in an incredibly ingenious way. Let's do what I love most. Let's take apart this technology, not with tools, but with thought. I want you to visualize the path of a single ray of light from the bottom of the screen to your eyes. I want you to see how a material that is both ordered and disordered can be the secret to controlling that light with micron precision. Don't worry about the complexity. We'll use analogies, as always. Let's think about fences, schools of fish, and sunglasses. In the end, you will not only understand how your screen works, but you will also appreciate the beauty of a universe that refuses to fit into our neat conceptual boxes. Nature is far more creative than we are. The first secret ingredient to understanding your screen is light, but not just any light, but a property of it called polarization. Imagine light as a wave traveling towards you. As it moves forward, it also oscillates or vibrates, up and down, sideways, and in all directions perpendicular to its path. The light that comes from the sun or a regular lamp is not polarized. Its vibrations occur in all possible planes. It's a mess. Now imagine passing that light through a polarizing filter. Think of it as a fence with very close vertical slats. Only the light waves that are vibrating vertically can pass through the slats. All the others, which vibrate horizontally or diagonally, are blocked. What comes out the other side is vertically polarized light. It's a more organized light. If you put a second polarizing filter in front of the first, but with the slats horizontal, what happens? The vertical light that passed through the first filter now encounters a horizontal barrier. Nothing gets through. It's all dark. Two polarizing filters aligned at 90 degrees to each other block all light. Keep this idea in mind, because it's the key to turning a pixel on and off. Now, the second secret ingredient, liquid crystal. What on earth is that? Let's use an analogy. Imagine a box full of matchsticks. If you shake the box, the matchsticks become a complete mess. pointing in all directions. This is like a normal liquid, whose molecules are disordered. Now imagine you manage to align all the matchsticks so that they all point in the same direction, and then you glued them in place. This is like a solid crystal, where the molecules have fixed and ordered positions and orientations. Liquid crystal is the magical intermediate state. Imagine the matchsticks still floating in the box, able to move and slide past each other like a liquid, but on average they all tend to point in the same general direction. They have directional order, like a solid, but freedom of movement, like a liquid. It's like a school of fish or a flock of birds flying. They move like a fluid, but all maintain the same general orientation. This orientation of the elongated molecules is the property we're going to exploit to manipulate light. The discovery of this strange state of matter was, like many great discoveries, an accident. In 1888, an Austrian botanist named Friedrich Reinitzer was studying a cholesterol-derived compound found in carrots. Upon heating the substance, he noticed something very peculiar. At a certain temperature, the crystalline solid did not melt directly into a clear, transparent liquid, as expected. Instead, it transformed into a cloudy, milky fluid. If he continued to heat it at an even higher temperature, this cloudy fluid finally became transparent. He realized he was witnessing a new phase of matter, an intermediate phase between crystalline solid and isotropic liquid. He shared his observations with a physicist, Otto Lehmann, who had a microscope with polarizers, and together they discovered that this milky phase was capable of affecting polarized light, a property thought to be unique to crystals. Lehmann coined the term liquid crystal to describe this paradoxical state. For nearly a century, it was a laboratory curiosity until engineers in the 20th century realized that this strange property could be the key to creating a new type of display. So, how can a material that looks like a milky liquid create sharp images? The genius lies in combining our two ingredients. The basic structure of an LCD pixel is a sandwich. On the back, we have a backlight. In front of it, a polarizing filter, let's say horizontal. In front of everything near your eyes, we have another polarizing filter, but this one is vertical. Remember, two 90-degree polarizers block all light. So, if that were all, the screen would be black. But in the middle, between the two polarizers, we place our liquid crystal layer. And here's the trick. The inner surfaces of the glass containing the liquid crystal are treated with microscopic grooves. The back layer has horizontal grooves, and the front layer has vertical grooves. The liquid crystal molecules in contact with the glass align with these grooves. The molecules at the back align horizontally, and those at the front align vertically. In the middle, the molecules arrange themselves in a beautiful helical structure, a spiral staircase that twists gently 90 degrees. This twisted structure is the key to everything. Now, let's follow the light. A beam of unpolarized light from the backlight passes through the first filter and becomes horizontally polarized light. Then this light enters the liquid crystal layer. As the light travels through the helical structure of the molecules, its own polarization is twisted. The liquid crystal molecules act as guides, forcing the plane of vibration of the light to rotate along with them. At the end of its journey through the liquid crystal layer, the light, which entered horizontally polarized, exits vertically polarized, having been twisted by 90 degrees. And what does it encounter? The second polarizing filter, which is vertical. Since the light is now vibrating vertically, it passes through it without problems. The result? The pixel is on, it appears bright. This is what happens when we do nothing. It's the natural state of the pixel. The light is twisted by the liquid crystal and passes through the second filter. But what if we want to turn the pixel off, make it dark? That's where electricity comes in, and the special nature of liquid crystal molecules reveals itself in its fullness. Let's look even closer, at the molecular level. The molecules that make up the liquid crystals used in displays are typically long and rod-shaped. They also have an electrical property called dielectric anisotropy. It's a complicated name for a simple idea. The molecule reacts differently to an electric field depending on its orientation. Think of the molecule as a small compass. When there's no magnetic field, you can point it wherever you want. But when you turn on a magnet, the compass needle instantly aligns with the field. Liquid crystal molecules do something similar with an electric field. To control the electric field in each pixel, engineers place transparent electrodes, made of indium tin oxide, in the glass on either side of the liquid crystal layer. When no voltage is applied, the molecules follow the twisted structure dictated by the grooves in the glass. But when we apply a voltage, we create a strong electric field that runs through the layer. This electric field overrides the influence of the grooves and forces all the liquid crystal molecules to align straight, like welded together, perpendicular to the glass. The beautiful propeller falls apart. Now we have the ability to control the pixel. The operating principle is the control of light twisting. In a pixel, when we want it to be bright, on state, we don't apply any voltage to the electrodes. The liquid crystal molecules remain in their natural 90-degree twisted configuration. Light entering horizontally is twisted 90 degrees and exits vertically, passing through the second polarizer. The pixel lights up. When we want the pixel to be dark, off state, we apply a voltage. The electric field forces the molecules to straighten out. The helix disappears. Now, horizontally polarized light enters the liquid crystal layer, but since the molecules are all straight, nothing happens to it. The light passes straight through without being twisted, and exits still horizontally polarized, but what it encounters at the exit is the vertical polarizing filter. A horizontal wave cannot pass through a vertical slit. The light is completely blocked. The pixel goes dark. By varying the voltage, we can even partially undo the helix, controlling the amount of light that passes through and creating different shades of gray. Combine 3 of these subpixels with color filters, one red, one green, and one blue, and you can create any color in the spectrum. You can do a stunning demonstration of this at home. Grab a pair of polarized sunglasses, most are. They act as our polarizing filter. Look at any LCD screen, your phone, your monitor, your TV. Now, slowly tilt your head to the side. At a certain angle, probably 90 degrees, the screen will go completely black. What's happening? The light coming from your LCD screen is already polarized, vertically in most cases. Your sunglasses are also polarized, usually vertically, to cut out horizontally reflected glare. When the 2 polarizers are aligned, light passes through. But when you tilt your head, you're rotating the polarizing filter of your glasses. When they reach a 90-degree angle relative to the screen's polarization, they block all the light, and the screen appears off. You're recreating the fundamental light-blocking mechanism of the pixel. This simple experiment proves that screen light has a specific orientation, a signature of the liquid crystal process that created it. It's physics in action, connecting your sunglasses, your screen, and the fundamental nature of light. The truly counterintuitive aspect is the very existence of the liquid crystal. Our minds are programmed to categorize the world into well-defined boxes: solid, liquid, gas, order or disorder. But nature refuses to be so simple. The liquid crystal is proof that reality exists on a spectrum. It shows us that a substance can exhibit properties of 2 different states simultaneously. It is the platypus of the matter world. Another subtle point is that the screen doesn't create darkness. The darkness is already there, potentially, in the form of the 2 crossed filters. The screen works in a subtractive way. The on and bright state is the complex state, where the liquid crystal has to do the work of twisting the light so that it can escape. The off state is, in a way, the simplest. The liquid crystal is forced out of the way so that the basic physics of the crossed polarizers can do its job of blocking the light. We are using a complex phenomenon to neutralize a simpler one. It's a dance of deceptions, a choreography of light and molecular orientation. Of course, this technology, however ingenious, is not perfect. One of the historical limitations of LCDs was viewing angles. If you looked at the screen from the side, the colors and contrast could change drastically. This is because the path that light travels through the liquid crystal helix is optimized for a frontal view. From an angle, the twisting of light is not as perfect. New technologies such as IPS, in-plane switching, have greatly improved this by altering the way the liquid crystals move. Another problem is response time. Liquid crystal molecules, although small, have inertia. It takes a tiny but measurable amount of time for them to twist and straighten out. This can cause motion blur in fast action scenes. Furthermore, because LCDs need a backlight that is always on, they cannot produce true perfect blacks. There is always some light leakage. That's why technologies like OLED, where each pixel is its own light source and can be completely switched off, offer superior contrast and deeper blacks. The importance of liquid crystals, however, goes far beyond the screens we use. This strange state of matter is everywhere in biology. The membranes that surround every cell in your body are, in essence, a liquid crystal structure. They are made of lipid molecules that self-organize into a bilayer, creating a barrier that is both structured and fluid. This property allows the membrane to be flexible, self-repairing, and to allow the selective passage of proteins and other molecules. Without the physics of liquid crystals, life as we know it, with its compartmentalized cells, could not exist. Similarly, long DNA molecules in high concentration can form liquid crystal phases. This connection shows, once again, a universal principle. Nature, whether in a man-made display or in the membrane of a cell evolved over billions of years, uses the same ingenious physical tricks to create structures that are both stable and dynamic, ordered and alive. And the physics that your screen uses to function also helps us see the cosmos. Light traveling through the universe often becomes polarized as it interacts with magnetic fields and dust particles. For example, when light from a distant star passes through a cloud of interstellar dust, the dust grains, which often align with the local magnetic field, scatter the light unevenly, polarizing it. Astronomers can measure this polarization. By doing so, they can map the shape and strength of invisible magnetic fields that permeate our galaxy. It's like using a pair of giant polarized sunglasses to see the magnetic structure of the universe. Similarly, the light from the cosmic microwave background, the remnant glow of the Big Bang, has a subtle polarization pattern that contains information about the universe's earliest moments, including clues about primordial gravitational waves. The same physics of light orientation that creates an image in your pocket allows us to reconstruct the history of our cosmos. This leads us to a philosophical reflection on our categories. We humans love to classify things: solid, liquid, gas, wave or particle, right or wrong, but nature operates on a continuum. It delights in intermediate states, in ambiguities, in exceptions that prove the rule. Liquid crystal is a humble teacher. It teaches us that our conceptual boxes are often crude simplifications of a much richer and more subtle reality. Our window to the digital world, our most modern tool, is built on a principle of fundamental ambiguity. And that is beautiful. It reminds us that the universe is not obliged to make sense to our limited intuition. It is up to us to expand our intuition and our imagination to embrace the strangeness and complexity of the world as it truly is. Reality is not only stranger than we imagine, it is stranger than we can imagine. And the screen in your hand is a small daily reminder of this profound and liberating truth. What does the future hold for this technology? While OLED and micro-LED screens are gaining ground due to their superior contrast, the physics of liquid crystals continues to evolve towards new applications. Imagine smart windows that can switch from transparent to opaque at the touch of a button, using a liquid crystal layer to control the passage of sunlight, saving energy on air conditioning. Think of sensors that change color in response to temperature changes or the presence of certain chemicals, all based on how these factors affect the liquid crystal structure. There is research into fabrics that can display changing patterns or colors, and even lasers whose beam can be electronically directed, without moving parts, using the optical properties of liquid crystals. Mastering this state of matter has opened up a range of possibilities that goes far beyond simply showing us pretty pictures. The ability to control light at such a fine level is a powerful tool, and we are only beginning to explore its applications. Even after more than a century of study, liquid crystals continue to amaze us. There are dozens of different types of liquid crystal phases: nematic, smectic, cholesteric, each with its own degree and type of order, and scientists continue to discover new ones. Understanding the subtle transitions between these phases is a profound challenge in condensed matter physics. How exactly do short-range intermolecular forces give rise to this long-range collective order? How do defects in the crystal structure form and interact? Will we one day be able to design molecules from scratch to create liquid crystals with any combination of optical, electrical, and mechanical properties we desire? These are the questions that drive cutting-edge research. Nature's toy box is much larger than we thought, and the impossible state of matter that feeds our screens is a reminder that there are still many secrets to be discovered at the frontier between order and disorder. So let's tie up the loose ends of our investigation. First, we learned about polarization, the property of light that allows us to filter it with oriented barriers, like a slatted fence. 2 filters at 90 degrees block the light completely. Second, we were introduced to the hero of our story, the liquid crystal, a paradoxical state of matter that is both ordered and fluid, and whose molecules can form a helical structure that twists light. And third, we saw the ingenuity of the combination. By using an electric field to straighten or relax this molecular helix, we can control whether the twisted light passes through or is blocked by the second polarizing filter. This is how a pixel turns on and off. The entire image on your screen is a vast array of millions of these light gates, opening and closing at dizzying speed, choreographed by a microprocessor. The lesson you can take home is that behind the simple and intuitive interface of your cell phone lies a mountain of physics and ingenuity. The next time you swipe your finger across the screen, remember what's really happening. You're interacting with an electric field that's aligning trillions of rod-shaped molecules to open and close microscopic gates for light. You're manipulating one of the most exotic states of matter to create an image. It's not magic, it's physics. But if you think about it, it might be even more impressive than magic. It's proof of the power of human understanding, of our ability to unravel the strangest secrets of nature and use them to build tools that shape our world and our perception of it. Your screen isn't just a window to the internet. It's a window to the fundamental laws of the universe and the limitless potential of the human mind. I want you to leave this conversation with a newfound appreciation for the complexity and beauty hidden in things we take for granted. It's easy to go through life without ever wondering how things work. But the joy lies in the question. The joy lies in discovering the hidden order within the chaos, the simplicity behind the complexity, and in this case, the coexistence of order and chaos in the same place. Nature doesn't care about our categories. It does what works. And by studying how it works, we not only become more knowledgeable, but also more humble and more amazed. So, stay curious. Keep disassembling the world with your mind. Look at a broken egg and wonder about the nature of time. Look at the ice floating in your drink and wonder how that accident made life possible. The universe is full of stories, and you have the most powerful tool to read them right there, between your ears. Now that we've unraveled the impossible physics of your screen, what other everyday paradox should we tackle? Should we go back and explore why ice floats, an anomalous phenomenon that literally saved all life on Earth from being frozen? Or perhaps we should investigate why you can never untangle an egg, a simple question that leads us directly to the nature of entropy and the arrow of time. Your curiosity is our compass. Leave a comment telling us which of these mysteries you want us to crack next, and the next time your screen turns on, smile. You're one of the few who knows you're looking at an impossible state of matter made possible through sheer human ingenuity.